We're good to go. That's a good time to say that all of these are recorded and put online, so you'll see us. That's the recording part. So for those of you who have not been to one of these before, the way it works is that we will speak up here for about 30-ish minutes, and then I'll open it up to Q&A for 15, 20 minutes, something like that. We'll keep going if people still have questions. But today we are lucky to have Dr. Lukas Taenzer here with us. He is a physical oceanographer working with our faculty member, Dr. Nicholas Foukal, who some of you might have seen speak a few months ago. So Dr. Taenzer earned his PhD in physical oceanography in the MIT Hui Joint Program in Massachusetts. A significant portion of his research is focused on understanding how offshore waters reach our coastlines and estuaries. He's also interested in how the offshore waters influence our fisheries and waters here on the coast. So please join me in welcoming Dr. Taenzer.
Thank you so much.
So to start off, I wanted to ask you a very seemingly basic question, which probably doesn't have that basic of an answer, but so what separates our water? I mean, the coastal water that we have in our rivers right here, and then the ocean water. I mean, is it one big thing, or is it separated somewhere? How does that all work?
No, I mean, it seems like a pretty easy question to answer because we can kind of think about like all ocean water is wet. I mean,
Yeah.
aside from perhaps the sea ice, that's not wet, but like beyond that, but like water has other properties too, or ocean water has other properties. So there is, for example, temperature. And we know, for example, that in the tropics, the water is generally like warmer than it is in the Arctic.
Right.
But on top of it, these like gradients or these transitions between warm and cold or productive and non-productive, salty, not salty, like these transition zones can actually be pretty drastic or pretty, like they can appear pretty sudden. And that's particularly when we move from our coastlines out into the ocean basins. So over here, I brought two photos. One is actually from a book cover on the left side, and the other one is a picture from satellites giving you chlorophyll A, which it basically picks up on the color that comes from phytoplankton or from productive cells in the ocean. And what I like about the left one, first of all, it kind of shows you our Georgia coastline. It shows you where we are, and then kind of from Florida up to Cape Hatteras. And when we move from the coast over towards the outer ocean, we see that there is this big transition in color. Kind of, it's like more cool. Like what we see over here is temperature. Like red means warm temperature, hot ocean water, and then green or bluish is colder. And so we kind of see like this transition period, which just kind of happens over a fairly short amount of distance. Similarly, when you look at the right side of the picture, when you look at the chlorophyll, there's as well, basically around all coastlines, it lights up green. And then when you look into the outer ocean, it's much more blue, which means it's much less productive. There's much less stuff growing there. And these transition zones where we change gradients very rapidly, we call that a front. And you don't just see it at the surface, you see it as well at depth. So here's a figure of how that looks like. Because what you saw so far, you saw the surface from satellite. But when you look at depth, what you typically notice is that these transition zones, they coincide with difference in ocean depth as well. So these very productive zones, typically less saline, less salinity, colder, they coincide with the continental shelf, so much flatter ocean. And then suddenly we move from the continental tectonic plate to the ocean basin plate. So that's where the continental slope hits, where you suddenly like go into the abyss and move from 100, 200 meters to like 1,000 meter, 4,000 meter depth. And so this zone where you suddenly change transitions, that's an ocean front. They span across many of our coastlines. And to come back to your question, I would call the left side coastal ocean, and I would call the right side the open ocean. And these fronts, like that's something where water typically doesn't, like it's hard for ocean water to kind of transition across that. And what I like to study is under what circumstances does it do that?
Yeah, so the first thing that comes to my mind, also growing up here in Savannah, is thinking about the currents in the Gulf Stream right off the coast of Savannah and how that warmer, saltier water comes into our water on the coast, if that does happen. So can you kind of explain how our currents, our major currents on the coast of Georgia and elsewhere, how those factor into the situation and how the water is actually brought onto our coast?
Yeah, for sure. Like when we go back to this figure over here, particularly on the left side, like yes, you know where the, like you've perhaps even seen a picture of the Gulf Stream. The Gulf Stream comes out of the Gulf of Mexico, comes around the Florida coast, and then hugs the coastline towards Cape Hatteras, where it then moves offshore, where it separates from the coast. But actually what's kind of cool is I talked so far about ocean fronts, like these transition zones in property, but they coincide as well with our currents. So kind of this place there where we move from less warm or cooler water towards warmer water, like that's as well the place of the current. And the reason for that can be actually explained with this figure over here. Because imagine you have such an ocean with like a front where water doesn't only have properties, but water has as well densities. And density is kind of in the end the property that we care about in physics, because different water of different salinity and different temperature has a different density. Mm-hmm. And now imagine you have water that kind of slopes like this, where you have the cooler, fresher water, which is typically the lighter water, and then the warmer, saltier water, which is the heavier water. Heavier because salinity has a bigger impact here. There's so much more salt in the ocean on this side than on this side. But now imagine you kind of try to build that in like a water jar at home. Like what would immediately happen would be kind of like this. Mm-hmm. Like the water would, like on the heavier side, would slump down and would try to get below the lighter water. The lighter water on this side would try to kind of to balance and would try to get here. So we need something that balances that. That's actually a current. Because of the Earth's rotation, currents in the northern hemisphere get pushed to the right. And so imagine now again the setting with the front. So this front tries to flatten. So now you have a current that goes against this force that tries to flatten it. And so you have this current that tries to steepen it. So if you have a current that goes towards me, that tries to go right because of Earth's rotation. So you have a force that tries to steepen the front, and you have a force that tries to flatten the front. And these two forces are balanced. So kind of any time when I'm talking about a front, I'm as well talking about a current. And anytime I'm talking about a current, I'm talking as well about a front. Like these things are very much entangled with one another.
Great. And this is a large question, so you can take it wherever you'd like to. But what is beneficial about the movement of water? I mean, you think about it in the major oceans, in the currents, or think about what's beneficial about how it's reaching us and what impact it has.
Yeah.
So why does our water need to move?
Our ocean moves because it's forced to. Like okay. It's kind of it can't otherwise. It's not like that's one of the reasons why, in my opinion, studying ocean physics is somewhat a little bit easier than studying ocean biology, because fish have a brain, and so they kind of it's hard to follow that one fish or think about what it tries to do in this moment. Mm-hmm. But water follows the forces you put onto it. And so you can study it, in my opinion, somewhat more easily with equations. And so in like basically the big engine in our climate system, what drives all of the currents, what drives all weather, and we can think of oceans kind of as ocean weather, is that like you have the sun hits the Earth, and more sun hits the Earth at the equator than at the pole.
Mm-hmm.
So you have the poles are colder than the equator. And so on Earth, you have the oceans and you have the atmosphere that try to mitigate that. Like the currents try to bring heat from the tropics towards the polar ocean. They're not doing a perfect job because not all temperatures on Earth are the same or are equal, but they are definitely pulling a lot of transport until an equilibrium is reached and until we are in a steady state. So that happens kind of on all of Earth. Coastally, for us, these like barriers are pretty important because fish, for example, are coastal, particularly benthic species. They like it cool. And so when we have now this big Gulf Stream water sitting offshore, it's kind of nice to have a current or a front in between that shields all of these coastal habitats off from all of this warm water. So that's as well one of the reasons why coastal waters can be so productive.
Great. So speaking a little bit more on a smaller scale, can you go into a little bit more depth about how the waters reach our coast and what influence that has on some of the habitats in our estuaries and that sort of thing, how it might influence fish and, you know, the coastal life that we have here?
Yeah, for sure. I think let me start with this one over here, since it's just up. I think like so far I talked about this frontal system as a barrier. Like it's a barrier that hinders water to cross it, which is its first order function.
Sure.
But and that's kind of how the front looks like. But then this front can become unstable. Like instabilities can form. Yeah, let me dig into this a bit more. So what I mean instability, like kind of could be a little bit understood as like when you think about a wave, let's say like a wave that's caused when you take a little dinghy or a boat just through the warm sea or out on the ocean.
Yeah.
And this little boat makes a wave,
Mm-hmm.
and these wave that kind of propagates out. And sometimes, I think you might have all noticed that when you stand on shore, sometimes the boat is gone, and then like a minute, two later, like that's really actually when you just start to hear the wave kind of reaching the coast. So there's a lot of time that can happen there. And what this wave does, it just transports energy. It doesn't transport the property. Like doesn't like when that water makes a little splash and there's this little wave forming, and later than 2 minutes, like when you then hear the wave crashing into the coastline, that's not the same water. Like it's not that water has then traveled to the coast. What actually happened there is that the energy transferred, which I found like when I learned about waves in my first wave physics class, I actually found there was a pretty profound thing that I hadn't really thought about, that like waves transport energy and they don't transport properties. However, like when you go out to Tybee Beach and you stand in the surf zone, you might have all noticed that like when you're kind of behind the surf zone, what the wave does with you, it just like bobs you up and down. But when you go into the surf zone, it does more. Like it kind of can really like slush you back and forth. So in this transition, in this zone where waves break, and where waves are not just like little small elongations, but where they like fully break, like that's kind of really where they can transport properties. So that's when we call waves nonlinear, while we call them linear before. And now you might wonder why I talk so much about waves, because this program is actually called Beneath the Waves. Let me now transition over. We don't just have these so-called gravity waves. Like what I talked so far about, we call that gravity waves, like where the gravitational force brings the wave up and down. And in physics, different so-called conservation properties can cause waves. For gravity waves, that's energy. Like energy is conserved, and so you balance between potential energy, that's up and down, and kinetic energy, that's movement. And then there are other conservation properties in physics. Like aside from energy, there's, for example, angular momentum is conserved. Like think about a figure skater. Like a figure skater, when they take their arms together and they rotate, then they speed up. Something similar can happen in the ocean as well. Like think about here a figure skater, like kind of in the center. And now that figure skater rotates and moves closer to shore. Suddenly the water column is less tall. So we squish the water column. That means that the figure skater rotates faster. Now we move the figure skater further offshore. It becomes deeper. We stretch the water column. So the stretching causes less rotation. And so we have, in order to conserve angular momentum, we have as well either the spinning up or spinning down effect of the water column. And so this exchange can as well cause waves along this frontal system. And I do have a picture of how that can look like. Like this here is again a thermal image on the left side. So thermal means it's as well temperature, but already a little bit older. So therefore you only see it in black and white. And then on the right side is a little schematic of how that looks like. So you kind of see that this front, like it's not just straight, it kind of has like little wiggles. And when these wiggles are not just like little wiggles as they are offshore, but kind of reach the surf zone state where they transition from linear to nonlinear, then they start breaking. And you can, for example, like see the upper white block in the thermal image. Like that, I feel personally looks surprisingly similar to a breaking wave that we all experience in the surf zone. So something like this happens as well on the scale of 10 kilometers, 100 kilometers. And it doesn't happen in the vertical, it happens in the horizontal, back and forth. So each of this breaking wave transports, because now the wave is not just transporting energy anymore, now it starts transporting as well material because it is nonlinear and breaks. So these are these moments when actually property can transition across the front and can then be exchanged between the coastal and the open ocean.
Okay, so how do you, as a physical oceanographer, how do you study this? How do you measure these things? Can you walk us through? I mean, that's very broad, but like, what are some of the instruments that you use, maybe in your own personal research?
Yeah, for sure. It's hard because like we are thinking here about these like breaking waves. They happen in 3 dimensions. Actually, they happen in 4 dimensions because time is as well an element here. Then they kind of happen intermittently. Like the reason why we talk so much about this balance is because it holds in about 90% of all cases. So only 10% of the time you're out, you will actually experience something like this. And so I think instrumentation-wise, it really depends on what you want to get out of it.
Sure.
Like if you are interested in kind of taking a census, thinking about how often does this happen, then a mooring is your way to go. Cause an ocean mooring, you put it out there. Like an ocean mooring consists of an anchor and a chain, sometimes a buoy at the top, and then you put instruments at the chain, and you bring it out, and then you go back to shore, and then you come back half a year or a year later. In the coastal ocean, you typically need to come back half a year later because there's so much stuff growing on it that you need to bring it back fast, and it's kind of a smelly affair.
Yeah.
When you steam back to the ship. In the open ocean, it's kind of tells you as well how much more productive the coastal ocean is. You sometimes get away with leaving it there for 2 years. So coastal ocean measurements, although they are so seemingly much closer, they are not necessarily easier because you need to maintain them more, and tides can be much higher, and there's a lot of more energetics involved. So that's kind of when you want to take a census, get a general idea of what's happening. If you're more interested in, like, we call that process studies. So let's say we want to look at the process of such an exchange, or this doesn't only happen at the surface, because at the surface we can now look at it through satellites, but satellites can't look into the ocean. So if you want to study that at depth, you do need to go out. Right. And then we use robots, like little, like either robots, which have the advantage that they're pretty fast, or gliders. Gliders are not as fast, but they have wings, and so they don't have a propeller, but that means as well that they save much more energy. So a glider can be out for like 2 to 3 months at a time, can just like transit back and forth. And so that can be kind of an instrument for combining both aspects of like getting a big overview, but at the same time measuring processes. And there's a pilot, and every time they surface, they send the data by a satellite back to you, and then you can give them new directions. Yeah, and then it's being out there with a ship and just sending something over the side and seeing what comes back.
Catherine Edwards' lab uses gliders for all of those who know her work too.
Which is extra hard because she steers them into the Gulf Stream.
Yes.
The Gulf Stream goes with like 1 meter per second minimum, and like the gliders, they are slow as well. Aside from the fact, they are pretty slow too. So you need to be kind of careful. So kudos to Catherine that she manages to bring them all back.
Right. So before I open it up to question and answer, I just wanted to ask you about what are some of the questions that you're interested in answering. Where is your research heading? I mean, you not too long ago finished your doctoral degree. So what kind of questions are you interested in answering?
Yeah, no, thanks for asking. So yeah, what I talked today about was mostly about my PhD topic, and I continue to be interested in that. But generally, as I try to think about what comes next, I try to broaden out a little bit and kind of get my feet wet in something else. I'm really fascinated generally by this question: how do we get stuff between the coast and the open ocean? Like that's kind of a theme I'm really interested in, and so I'm really looking forward into doing that in fjords, because particularly like around Greenland, because there we think not just about questions about fisheries and how do we bring nutrients from into the coastal ocean, how do you preserve habitats, but that's as well about how does the fresh water that comes from the glaciers that melts, how does that get to the open ocean? How does the warm water that has the melting potential, that can melt the ice, how can that go into the fjords? So in fjords on top of it, it's not bringing it from the shelf break to the shelf, but it's kind of stretching further inshore into estuarine landscape, which is something I haven't encountered before.
Yeah. Great. Well, thank you. We'll turn these off so we can go to the overhead mic. And we have some time for questions. So if anyone has a...
Yes, hi. Thanks for your talk. Very informative. How do hurricanes impact the zone between ocean water and coastal water?
Good questions, but particularly here, because we are in a hurricane zone. I was talking about the waves earlier, and if you're thinking about, like, again, the analogy with the boat, like you have a boat that passes through and that causes a wave. If we're thinking about the ocean, we need as well something that we call forcing that can cause the wave, and that can be, for example, a storm, or particularly a very big storm, or for example, a hurricane. And so we can think of those as initiators of these waves. And regularly, they cause these waves to be so strong that they are immediately nonlinear. Sometimes a weaker storm causes the wave to be linear first, and then as it progresses, it becomes nonlinear. So you get that would be one of the examples how hurricanes affect the coastal ocean. Then, like, that's kind of particularly thinking about these frontal systems. The big other one is mixing. You, particularly in the summer, like when I'm show you this figure over here on the left side in temperature, like I can tell you that this is not recorded in the summer, because in the summer we wouldn't see this in satellite pictures. Because what you would have is you have a very hot surface layer that was heated by the sun, and then you have colder water below. And so you still have this picture below in the depth, where the coastal ocean is typically cooler and the open ocean is warmer. But at the surface, it all kind of looks the same, because there's just so much more heating coming in from the sun. But what the hurricane then does, it mixes all of that up. It makes the water column more homogeneous.
Question. So you're talking about waves being generated between the atmosphere and the ocean, and then you're also talking about different layers in the ocean with different densities. Do you get waves inside on those interfaces as well?
Oh, yes, for sure. So these are called internal waves. So you have the waves at the surface. So we have a multitude of different waveforms. So yes, there are the surface waves, like thinking just about gravity waves here, like the normal ones up and down. But what can happen as well, either as well storm forced, or when there's flow going over topography. Like let's think about flow going over the sill, and then kind of falling down on the other side. Suddenly you have as well a starting point, similarly to a boat passing through. Like that's a starting point for a wave. And so you have these internal waves, which are caused by the density differences between different layers. And because at the surface, the density difference between the ocean and the atmosphere is kind of everything. Like water has a density of 1,028 or 1,025 grams per kilogram per cubic meter, roughly. Air has about 1. So you have like a difference of 1,000 kilogram per cubic meter. But the difference in density between different ocean layers can be like 1 or 2 kilogram per cubic meter. So your force that forces the water that you brought just down back up, like kind of the buoyancy force, is much weaker within the ocean, or between these two different ocean layers. And so you can have massive internal wave amplitudes, like 100 meter easily, while we wouldn't see this at the surface. Like that's more like a meter. Yeah. Questions? Sure.
Yeah, as the ocean warms over the next 20, 50, 100 years, what will happen to that the boundary between coastal and open ocean?
That is a good question. That I don't have a good answer for. But let me. So there are definitely models. There are definitely models out there that run. So like I don't know whether you've heard of, like there's the IPCC report and this so-called CMIP. It's like the coupled model intercomparison project, where global models, coupled models, atmosphere, ocean, and other climate components all run different scenarios depending on how much greenhouse gas we all put into the atmosphere. So there's that kind of uncertainty in there, and they calculate it for different scenarios there. I don't know exactly what these models say about like the Gulf Stream front there. I think the issue is a little bit that the models are still too coarse to kind of show you that on this scale. But I am pretty sure that there will be a Gulf Stream, because the Gulf Stream is generally wind-driven, mostly or predominantly wind-driven, and that will continue for sure. And with the Gulf Stream continuing, as I was saying, as well a front coinciding with it, so there will be this barrier. There might be a tendency, it might be a little bit stronger, it might be a little bit weaker. I can't speak to that right now, but this barrier itself will be lasting. Yeah, it's lasting.
To what extent does like upwelling and downwelling have in relation to like the wave fronts and currents?
Yes, up and downwelling. So just to perhaps clarify what we are talking here about in terms of So what can happen in certain regions and these are predominantly wind-driven, is you have wind in a certain direction that, like when you have wind over the ocean, as well because of the Earth's rotation, the ocean reacts to that. And the ocean doesn't actually, in the large scale, it doesn't react to it like I push the wind and then this is where the water goes. It's like I push the water in the northern hemisphere and then the ocean goes that way because of rotation. This is called the Ekman effect, or the so-called Ekman transport. And so, like particularly of, for example, of California, the winds are in that direction that they push the water away from the coast, and so that water needs to be filled up, and that happens from below. And so that's called upwelling. This here is not like what we see over here. This side wouldn't be an upwelling or downwelling side, because here we kind of work more with these shelf break fronts that doesn't happen as coastal. But what does, for example, happen in the region that I did my PhD on, which is the northeast shelf, or the so-called mid-Atlantic divide. That goes everything from Cape Hatteras over to the Gulf of Maine. Well, very productive fishing zone. Like there, you have as well upwelling, but you don't have it at the coast. You actually have it at the front. And so the reason for that is that the reason why these frontal systems are stuck at the shelf break, where as we remember, the ocean depth suddenly drops, like we move from the coastal ocean towards the deep ocean. That's like really where these shelf break fronts are stuck. Like that is because of dynamics in the so-called bottom boundary layer, or like in kind of the 10 meters below the ocean floor. And what happens there is that water gets faster pushed offshore along the coast because the ocean is just not as deep. And so it feels more forcing from the top than over the deep ocean over here, because kind of the entire effect stretches across a deeper water column. And so you create convergence at the bottom, like where you push more water offshore over the coast than over the deep. And so that excess water needs to go somewhere, and it goes up. And it brings nutrients with it. And therefore, we generally see a bunch of, like a lot more biology in those regions. It's actually, I forgot to show you this as a picture, but I hijack your question to show you this, because I think it's pretty cool. What I show over here is the Patagonia shelf. So, different hemisphere of Argentina. And on the left side, I show you chlorophyll. It's again phytoplankton, so how much so-called primary productivity there is. And then on the right side, I show you a picture that just shows you light, like just light from space. And do you see this like band lighting up in? I mean, like this is not satellite measures something and then using like some complicated math and transferring it into another variable. This is just light, and it's fishing boats. It's squid vessels. Like squid are getting fished by putting a ton of light onto the ocean, and then the squid come up because they think like that's where like they're attracted by it, and then they're being fished. And so both this line where all the squid vessels are coincides with the line where there is a lot of chlorophyll, and all the lines with the position of the shelf break front, because there's upwelling, and that's where everything gathers together on multiple trophic levels. So I really like this right panel picture. So thanks for reminding me.
Anybody else?
So how does all this affect when we have rip currents here?
When we have rip currents, yes, that is a good question that I feel very ill-equipped to answer. Because everything that I do kind of happens in water 50 meters and more, like where the so-called boundary layers don't meet. So we have in the ocean two frictional layers. Like there's a frictional layer at the top, influenced by wind, mostly, and then there's a frictional layer at the bottom. So where we feel the bottom influence, and then the further we move towards the coast, and at some point they meet, and that's where the magic happens. And it's kind of its own subfield. Like coastal dynamics is really hard. And some really good engineers do that pretty well, but I think I'm fairly ill-equipped to do that. I don't think that these exchange mechanisms that I do look at, that they really affect rip currents super coastally. I think like rip currents are affected by they're affected by local conditions, like local winds for sure. They are as well affected by waves. And these waves can sometimes be caused very far away, and then they can travel long distances. But these waves, again, because they transport properties, they transport energy, they can just make it across the front. Like they're not hindered by it. And so I think there's kind of that separation. But kind of making it a couple of degrees warmer or bringing more nutrients in there or exchanging properties, I wouldn't necessarily see a strong connection there. Thanks for asking.
I was curious about your career path. Like, how did you end up studying physical oceanography? Where did that start? I guess from undergrad.
Yeah. No, thanks for asking. It's a good question. I haven't answered that in a while, I feel. I studied physics in undergrad. And that was mostly because of a really good physics AP teacher in high school. So it's kind of like how it typically goes. You have a really good teacher who really she had like so many experiments with us, and I think she really brought fascination for the scientific method. Like it wasn't kind of like here are the facts. It was like kind of we as a class, like we went through like the photoelectric effect, which is kind of like the basic, like the fundamental aspect or the fundamental experiment that brought up quantum mechanics. Like we redid that in class, and that was just a really cool experience of kind of like not redeveloping but refinding that law with connection. And then at some point I was always interested in the natural world, really enjoyed hiking and really enjoyed kind of being outdoors, but not necessarily too connected to the ocean, but just came across some articles in like a National Geographic that talked about the jet stream. And the jet stream is this band in the atmosphere that is this well kind of front and the wave across. And then I read somewhere else that 90% of the excess heat from the atmosphere, or that from the excess heat that's being trapped under climate change actually doesn't end up in the atmosphere, but it goes into the ocean. And so, well, I feel like studying a reservoir that takes up 90% of the heat, of the excess heat from climate change, that's a pretty important place to study. And so I drifted over there, read a little bit more, applied to grad school, and came to that. Like serendipity is a thing. Like I feel like if I haven't read that article, perhaps not. Yeah.
One or two more.
I was wondering in your studies if you've seen any impact from sarcasm on imaging or transportation of property because it's in the southeast is becoming more abundant.
Yeah. Good question. I've read the articles as well, like particularly like the ones in Florida. When was this? 2023, like summer with with the tons of sargassum there. I might be wrong on the year, but I haven't in my research. I've only encountered it just being out at sea. Like it's remarkable how patchy the ocean is sometimes. Like we not just in terms of these gradients, but like first of all in like color. Like the ocean just like has a different color when you cross these fronts. Like, it's kind of like more green, more murky, and then like I don't know whether any of you go like open water fishing. Like, the ocean has a different color. Like it's just like much more blue, and you see like much deeper when it's empty. And similarly, we were at sea, and sometimes it's like crossing into a patch where there's just like so much sargassum, it's just everywhere, and then it's like blew out and not anymore. And I think that really speaks to the fact how like sometimes very local conditions in like local upwelling and local productivity can like cause these blooms in places. Yeah.
Do you think what is the temperature that you're talking about, the increase expertise absorbing of that condition for that particular more, the sargassum? So that's something probably.
Yeah, people talk about that for sure. I'm unsure right now how the relationship looks like, particularly for sargasso. So I don't want to say something wrong right now. But yeah, no, there is for sure a relationship between, like, for example, there is one for jellyfish and yes.
Well, my question is not the same, but kind of similar, like that beautiful green nutrient-rich band that surrounds the continents all around the globe. As the ocean temperature shifts and changes, what's going to happen to that? Well, if that warms too much, the inner side of the shell, and that kills that phytoplankton or whatever, will it ever grow out, or will it always just be shrinking in? And I don't know if that's a good way to ask.
With phytoplankton in general, it really reacts to conditions that are just like when the conditions are right for phytoplankton to grow, it will grow, and it like goes through the roof. And like what phytoplankton is just like really good at, it's like at the moment there are the nutrients, it grows and it takes up all the nutrients, and then like it's nutrient depleted. So that's for example why we see these blooms in the first place. Like there's the spring bloom and then there's a fall bloom typically. The spring bloom is caused by there's suddenly against like enough sunlight that phytoplankton can grow. And then for the summer, all the nutrients are depleted. So it's not necessarily related to temperature. Temperature are just like very hot, very warm there. It's more like nutrient availability. It might change perhaps the speed of how much it grows, and different species have different species like different temperature regimes more than others. But then it's really kind of more driven, like the existence of a bloom is more driven by how much nutrient sunlight are available in this particular place. But there are these these toxic algal blooms, for example, where the thought is that they relate to the blooms, for example, and they are different properties. There was like a really there was a tripos bloom which has like kind of very big phytoplankton cells, which other organisms like zooplankton didn't really like to consume, and so they hung out a lot in the water column. That, for example, happened in the Gulf of Maine just 2 years ago. It's like a big event that clogged filters and that kind of stuff. So this, the ocean gets weirder. It doesn't necessarily change the being phytoplankton, but it definitely changes the type and species that you see. Yeah.
Any last questions?
Do you know of any hurricane that's ever crossed the equator? Ever?
That I don't know. I don't know how my head.
All right. Well, thank you very much.